Well, today we're dealing with concrete technology, maybe one of my favorite topics here. So we'll deal with concrete safety at first, just a little bit. We mostly do that in construction safety. And then we'll look a little bit at the chemistry involved in concrete. Concrete is a chemical reaction. We'll deal with the making and placing of concrete formwork and concrete reinforcing, and finally the jointing of concrete. Concrete is not the same as cement. Cement is one of the ingredients of concrete. Concrete is a mixture of gravel and sand, the Portland cement, which is the binder, and then the water. And the Portland cement and the water, they chemically react with each other to basically glue the gravel and sand together. It's the adhesive that glues all these parts together. The strongest concrete mixes have lots of gravel, some sand, the Portland cement that you need in order to take care of the binding of all these materials together with the water. But if you add too much water, more than you need for the chemical reaction, you weaken the concrete. And so you need to have a lean mixture as far as water is concerned. Okay, then third bullet down, concrete hardens by a chemical reaction that we call hydration, or sometimes we refer to the Portland cement that we use in concrete. It's called Portland cement, is a hydraulic cement, but it's the chemical reaction is hydration, or sometimes we talk about hydraulic reactions. So because it's a reaction with water. And there's actually a heat generated by this chemical reaction too. It's not very measurable in day-to-day examples, but it is a true thing. And when you start running a very high-speed, quick-setting cement, you can feel the heat. Cement is also, in this chemical reaction with water, a toxic material to us, to our skin, in terms of burning the skin. For most day-to-day exposures to concrete, it's a matter of whether you're marinating it, and it's not a matter of accidentally getting some on your skin and oh no, it's just that if you're leaning into it, if you've got a bunch of it in your boot or inside your gloves and you're just kind of holding that against your skin for a period of time, the cement can start reacting with the water in your flesh. So yeah, we've got some pictures of concrete finishers, concrete placers actually at this point, and probably finishing too. But here is an example. You get some concrete in your boot and you could get a wound like this. That could be a chemical burn here. Looks like there might be a little infection. In an open wound, the Portland cement paste can turn into a blood poisoning in here, so that you could actually be in danger of you losing a leg over that. And then some people get kind of irritant reactions to the cement against their skin, either the paste or the powder, and they call that a cement dermatitis. And then if you're breathing in the cement into your lungs, well, there's silica in there. Also, if you're breathing it in through your mouth or your nose, where the moisture is at in the back of your throat or in your nose, you can end up getting chemical burns in the nostrils or in the back of your throat from the same chemical problem here. Here's some uglier wounds, especially that bottom left picture where somebody was kneeling in the concrete throughout the day. Some of these you can see at the the bottom left, serious burn. The upper left is less serious, and that's a lot of it is right there at the sock line. And then at the upper right corner, we're seeing the actual burn that might happen if it was getting inside your gloves. And so, yeah, it can be a serious thing. And then if you get any of this paste in your eyes, that can sting and that can hurt. So you've got to wear goggles, safety glasses, and maybe goggles, depending on what you're doing. A concrete pump or a bucket or a concrete chute or the vibrator can splash this stuff up into your eyes. Okay, so the thing about concrete is that it's different than other kinds of activities we do with welding and steel or woodworking and wood. This joinery is a little different than actually forming material. We go and build these temporary forms that have to be strong enough to support this material. while it's setting up, and then it has to be easy to strip, and so we need to remove those forms. So looking at these points here, the last things about safety that I'm going to talk about in here, and that is that the faster the concrete is poured, the greater the pressure on the forms, and those forms can burst. Rebar, reinforcing, you can be impaled by the rebar. So then you've got the problem there. So we put plastic caps on the rebar. Tilt-up wall panels, lift slabs, precast concrete is all preformed concrete in some way that we're picking up and placing somewhere, what we call erecting the concrete, must be placed and braced properly and to avoid collapse. And of course, because it's so heavy, when it collapses, it kills people. Tools and equipment, there's various hazards in there too. We're dealing with unique kinds of equipment, from power trowels to automated vibrating screed systems and placers. And then, of course, the cement dermatitis that I mentioned. There's they're using the right personal protective equipment like rubber gloves, goggles, glasses, rubber boots, long pants, long sleeves, a respirator if you're dealing with concrete dust, which is full of silica. Okay, and then one other thing I just kind of tacked in here was to talk about tremie pours. A tremie pour is normally where we're pouring concrete underwater. And so the most common way to do this is filling a snorkel, filling a funnel, funneling it from, let's say, a chute of a concrete truck, or in this case, I've got a belt, what do you call it? Conveyor belt, yes. Anyways, yeah, the word was right in front of me if I looked at it. And it flows down into a wall or flows into underwater. Try to reduce the amount of mixing with the water when we're building a foundation for a bridge or something. But it is possible to use a concrete pump, and that's the one I wanted to draw attention to. Using a concrete pump to pour concrete underwater, the pressures are such that you can launch the snorkel, and if you're hanging on to the handle of the pump to direct it, you could go for a 50-foot ride, and maybe strike something or somebody. That can be a very, very serious or deadly accident because of that. So you have to be very careful. So we do pour concrete underwater in foundations, either mostly the top method that you see in this little diagram, where they're pouring it down through the hopper or the funnel, and then it oozes down through the tremie pipe, and that reduces the mixing and keeps us from separating. And so we typically try to keep the snorkel or the hose or pipe within the body of the mass of concrete. As soon as you've got a bulge in there that you can insert the pipe into, that changes, that helps a lot. With a concrete pump, it is really, really important that you keep the end of that pipe within a bulge of concrete, within it, because the pressures are less as long as the snorkel of the concrete pump is in the actual concrete pile that's underwater, I mean. Okay, so that's enough about tremie pours. So again, working with concrete is more complex than working with other kinds of construction materials. That you're not involved with there's so many other variables that can throw things off. Slightly different conditions can change how fast and how well a particular mix places that day, how well it finishes, how well it cures. And so there's just slightly different conditions can affect how serious the dangers are. And also when there's an urgency, when the concrete's setting, it's all hands on deck and people start rushing. And so we're always taught to walk methodically on job sites and to not rush, because when you rush, people get hurt. But when you've got the urgency of concrete setting up, sometimes that's thrown to the wind and people start doing haphazard things because of the urgency, and then people get hurt. They trip on things and everything else. Okay, so the chemistry of concrete. Let's look at that a little bit here. Anyways, I've got more stuff in here than I can possibly go through here, but the earliest concrete that we really know of historically, maybe 300 BC. So we're talking, what, 2,400 years ago. The Roman empire had a understanding of how to make concrete. Now, they didn't know how to make the cement, but they knew how to find some sources of natural cement, basically from a volcanic ash kind of source. And so they were basically using a volcanic ash that they were able to use. I think mostly originally in the area of around in some places in Italy, where they could take something with high silica and alumina content, and they made some excellent concrete that's still around today. So, and there were some other cultures around the world that discovered this too. So it's been, to figure out who started this whole process. But of course, the Roman Empire was huge, and so they did a lot of it. But with the fall of the Roman Empire and a lot of these civilizations, a lot of this understanding was lost. But that said, nobody knew how to make the actual cement, the hydraulic cement that we use to make concrete, until this guy in England, Joseph Aspdin, he actually patented his process in 1824, and he called it Portland cement because there was a quarry, a rock quarry near where he lived called the Portland Quarry, and so he called it Portland cement. So that's where it got its name. Portland cement is just, that was his name, and it's used to this day. And so often we capitalize it because Portland is a proper town, a proper, in England, and a couple of towns, significant cities really, in the United States, one on the East Coast, one on the West. But anyways, basically the secret to his success was he was taking all these finely ground materials that were really part of the original materials, very much like the base materials that the Romans were using, but he heated them up to about 2,700 degrees. And that's what chemically changed this material so that it actually had hydraulic properties. So anyways, that's what we use today. Basically, we have some varieties to it, but it's all basically that basic principle. And then technology changed a lot in the 1800s. We had 1850s. There was actually 1892 is when there was a French person, Francis or Francois Hennebique. I don't know if you pronounce that exactly, but in 1892, he patented reinforced concrete. So that concept of reinforcing concrete by embedding or imparting inside of the concrete as you placed it and such, steel reinforcing. And we still use that concept today. Now, there's things that we've improved upon. They might have just been using simple steel and bonding it. Modern times we put bumps on the rebar so that it binds and bonds better. And then, of course, we've gotten more advanced with post-tensioned and pre-tensioned concrete, where we put the steel under high tension, and so that it actually actively is compressing the concrete. And that means the steel is actively working. Okay. In modern steel, you've got these bumps on it. And it's basically all steel that we have is round nowadays, the round bars, all the rebar. And it starts off as round, smooth bar. And then they run it through a machine and put bumps on it by squishing it. And so a 1/2-inch diameter bar might have been exactly a 1/2 inch when it went into the machine. When it comes out the other side, it's less than a 1/2 inch between valley to valley on the bumps on the bars. And from mountain peak to mountain peak of the bumps of the bar, you get more than 1/2 inch. So when you go to measure a bar, you have to kind of take a bit of an average. In this picture on the left, we're looking at 2 mats or 2 walls. We call them mats often in construction, even when they're vertical like this, of steel in this wall. And then in the upper right-hand picture, we've got 2 horizontal mats of steel. And so a lot of times in your experience in construction, you may find on jobs where they only use 1 mat. Well, in a 4-inch thick slab for a house, for instance, slab on grade house or a driveway, when you're only pouring 4 inches, there's not enough room for more than 1 mat. And that's the only reason there's 1 mat. We need to get it up off the ground, and you need to have about an inch and a half of coverage on both sides. And so by the time you have, let's say, 2 1/2-inch bars together in a 4-inch slab, and you need, an inch top, an inch bottom at least, you're talking, there's no room for another mat. And so that's why we put it in the middle, and it works half as well as it would otherwise, but it's far better when you've got thicker concrete to have a mat closer to one side and another mat closer to the other side. You need a certain amount of coverage around every bar. But anyways, I'm getting off topic here. So let's move along here a little bit. When we're looking at the ingredients of concrete, there's the fine aggregate, that's the sand. There's the coarse aggregate, that's the gravel. Well, we talked about that back in the foundations chapter in chapter 2. But the coarse aggregate is what we have the largest ingredient of in concrete, and then the second largest amount of material in the concrete will be the fine aggregate, the sand, and then the third largest quantity of material in the concrete will be the Portland cement, and then you got the water would be the least of those 4 basic ingredients. But the basic 4 ingredients of concrete would be the gravel, the sand, the Portland cement, and the water. So you might have, let's say, 1,800 pounds of gravel in a cubic yard of concrete. You might have 1,300 pounds of sand in a cubic yard of concrete. You might have 500 pounds of cement in there, maybe 250 pounds of water. So we measure the ingredients by weighing the ingredients. Typically in a ready-mix factory, we're weighing a ready-mix plant. When they're mixing the concrete into a ready-mix truck, they are mixing up the ingredients by weighing those ingredients. So in this slice here, the larger nuggets you see, that would be the gravel, and then there's some smaller nuggets you can still see that are getting down into the category of sand particles, and then there's some gray mass in between the sand particles, which are really the cement paste in here. The cement in the mining process of getting calcium silicates and lesser amounts of compounds like aluminum and iron and magnesium that are in the mix. They'll take raw materials from sources like limestone, chalk, marble, sea shells, clay, shales, industrial waste materials sometimes, iron ore, bauxite, all kinds of ingredients are part of this. But the basics the main thing is we got a whole bunch of calcium silicates that are all part of this. And so they grind it up into smaller and smaller particles. And then eventually they're running this stuff through a ball kiln where they basically have some ceramic balls that are rolling around in a big rotating pipe on a subtle angle, slow angle, so that as it's rotating, it's continuing to keep the material from caking up as they're heating it up to about 2,700 degrees. And as it comes down the other side and cools off, and it's still all about keeping it from caking up, eventually it's kind of collected at the other end and eventually put into either bags or a bolt truck, a bolt car, a box car. And a lot of the stuff, in order to move it, they pump it. But of course, it's a powder, so they're really just vibrating it and blowing and pumping it in various ways, but mostly by vibrating it, keeping it airborne, and moving it almost like a liquid, but it's all just a big bunch of very, very fine powder. Now, you should know the standard weight of a standard bag of Portland cement. Now, some of you may have worked with pre-mixed concrete bags that already have the gravel and the sand and the Portland cement in them. So the standard weight of the full-size bag for a bag of pre-mixed concrete without the water, but everything else, is 80 pounds. And then there's a 60-pound bag, or you can even find a 40-pound bag, but probably the 80-pound is the most common. Maybe at the home center, a 60-pound bag is pretty common too, because it's not so heavy to kind of pick up, move for some of the less athletic customers. But that's different than a bag of Portland cement. A bag of Portland cement is 1 cubic foot of volume. 1 cubic foot of volume in a bag of Portland cement, and so it's exactly 94 pounds. And I say that, but there are some varieties of Portland cement that could be 92 pounds. But we're going to stick with one number to keep it simple. That's what traditionally, in all the textbooks, they will refer to the weight of a cubic foot of Portland cement, which is what a bag of Portland cement is, as being 94 pounds. And you need to know that. When you're mixing up concrete in a volumetric mix design, where you're mixing not by weight, but by volume, then the bags are really important. So you'll find that people, especially old timers, will talk about, oh, that's a 5-bag mix or a 6-bag mix. And that tells you something about the strength. The more Portland cement you add to concrete, the stronger the concrete becomes. And so a high-strength concrete mix could be a 5-bag mix or a 6-bag mix, whereas regular concrete that you're using for foundations be more likely to be a 5-bag mix. And so they're referring to 5 cubic feet of Portland cement inside of a cubic yard of concrete. Remember that a cubic yard of anything, whether it's concrete or Chuck E. Cheese balls, is 27 cubic feet. Okay, so here's something I wanted to aside. This is a close-up picture of a slice through some concrete. In fact, the large nuggets that you see up at the top are gravel pieces that you can't even see the whole piece of gravel in this picture because we're just that up close. So the nuggets that you can see full size are actually sand particles. And then you'll notice that there are some tiny, tiny, tiny little dots in there that are actually air bubbles. Those are not normal air bubbles that you would normally be vibrating out of the concrete. Those air bubbles would be much larger. These are what we call air entrainment. We artificially add air into a concrete mix through an additive that creates these air bubbles, tiny, creamy air bubbles. I say we do it, but we don't really do it a lot in Louisiana because the main reason for air entrainment, air bubbles in a concrete mix, is to protect the concrete from freeze-thaw cycles over the years, long after the concrete's set up. And having those little tiny air bubbles are like little cushions, little airbags or something. I don't quite understand the concept in my head, but they've been able to prove that this helps to make concrete bridge decks more durable to the freeze-thaw cycle in the wintertime in places in the country that have that issue. We just don't have that issue enough here to worry about it in Louisiana, so we don't tend to use a lot of air entrainment in here. But it's worth mentioning so that you understand this terminology here, because it does change. When you add air entrainment, it does make the concrete more flowable, as if it has water in it, more water in it, so it's more flowable. But it's not a great way to do water reducing, because normally having less water in the mix will make it stronger. But if you're replacing it with air entrainment, the air entrainment is also weakening the concrete too. It doesn't make it stronger overall. It just makes it more durable to the freeze-thaw cycle. But it does make it easier to place. It's more flowable as you're placing it. But there are better ways to deal with that. Okay, so the air entrainment is usually kind of pay attention on by a certain percentage of material. So you might have somewhere between 2 to 8% of the total concrete volume in air content. And so that's how we refer to it. Okay, so this page here is an important page, feature-rich, because you need to kind of know some basics about these different types of Portland cement. The most common one by far that you'll ever deal with is type 1. And so you see these are all in Roman numeral style. So we got I for 1, II for 2, III for 3, IV for 4, V means 5. So, 1, 2, 3, 4, 5. There's 5 types of Portland cement in general. But then you see the 1A and the 2A and the 3A. The A stands for air entrainment. So you can buy cement that already has the air entrainment additive as part of the material. It's built into it. So that's one way to do it. But in all the concrete that I've had anything to do with mixing, and I've started early and I did a lot of it, many thousands and thousands of cubic yards of concrete that I've mixed or placed or both. We've never used any of these type 1A, type 2A, type 3A. We use a separate additive that we would add to the mix instead. And so, so this is just a thing. But anyways, so type 1, you should know that's type 1 normal. There's type 2, which has moderate. You see, if you go down to number 2 on the table, moderate resistance to sulfates. There can be sulfates in the soil, chemically unbalanced, where they can attack the soil. The soil can attack the concrete. So the soil itself, we're not talking about the gravel and the sand in the concrete mix. We're talking about the soil that you place your concrete foundation into, but the sulfates can damage the concrete over time. So what we've got now is that all type 1 cement, mostly, I say almost all of it, pretty much all that we can access in this country anyways, is rated as both type 1 and type 2. So they've kind of gotten rid of a product by combining these two together. So most bags of Portland cement that you buy will say type 1/2. And so that kind of means that, you don't have to worry about type 2 so much. Way down at the bottom, type 5, type V. Type 5 is high resistance to sulfate attack. That one still exists, because if you've really got some serious sulfate problems in the soil, then yeah, you probably will. So it basically works similarly to type 1 cement, but it has the resistance to the sulfate attack built into the concrete. Okay, so we've looked at type 1, type 2, and 5, but so we got 3 and 4. So number 3 is high early strength concrete. It basically, we speak of concrete being fully cured after 28 days. In reality, is it keeps getting stronger long after 28 days, but that's when it's officially considered cured. And so everything we talk about, the final strength of concrete, is after 28 days. But so when we look at type 1 and type 3 cement, they have the same strength after 28 days. So, but the big difference is that the type 3 cement will get strong early. In the first week, it will be a lot stronger than the type 1 cement. And so in precast concrete plants, they often will use high early strength concrete because they need that concrete to get strong enough so that they can take it out of the form and make some more concrete in that form. Because once you pour concrete in a form and you're waiting for it to set up strong enough so you can pull it out of the form or remove the form from it, whatever, and start again, and so you can use those forms again. And so it helps with production. So that's the main reason. It allows you to pull that girder out of the form and stack it away or put it on a truck or whatever you want to do a lot earlier. So high early strength is for that reason. And then there's one more cement here, type 4, that I haven't talked about, IV, or type 4, down here at the bottom, near the bottom. It says low heat of hydration. When we're pouring massive amounts of concrete, where it's very, very thick concrete, let's say 10, 15 feet thick, maybe 60 feet thick, whatever, for a hydroelectric dam maybe. That heat that I was talking about, that is part of the chemical reactions in this concrete as it's setting up, that starts to be a factor when you got massive amounts of concrete collected together. The heat starts to build and cause stress cracks and that sort of thing. And so it's a little slower setting, but it basically is all about slowing down enough to reduce the heat so it's at a controllable level when you're dealing with mass concrete like hydro dams and stuff. Okay, so when we were dealing with masonry cement, we had the different types of masonry cement. That was all about the amount of hydrated lime mixed to type 1 cement. So all masonry cement is type 1 normal cement with different amounts of hydrated lime. And so we had M, S, N, O, K for the different types. Those were all in alphabets, using the alphabet. Here we're using Roman numerals. And so in cement, it's all type 1, 2, 3, 4, and 5, all in Roman numeral form. Okay, so that's enough about that. 90% of the manufactured cements that we use generally are in the type 1/2 category. That's all it's saying in here. Now, there's about 900 pounds of carbon dioxide created into the atmosphere for every 1,000 pounds. So almost a 1-to-1 relationship of Portland cement that's created at a cement factory that makes Portland cement. And so There is an environmental concern here. Now, they're getting better and better every year at capturing that excess carbon dioxide to keep it from going into the atmosphere. But it has been traditionally um, a problem when it came to, these additional release of, of this gases that are greenhouse gases, basically. So it's something to be aware of, but they're trying to address it. Let me kind of skip along a little bit more. You see how I got a beaker full of gravel and a beaker full of sand here? And you would say those containers are full, but in reality, when you look at the beaker full of gravel, you can see all the air voids in that. And so you can fill that with sand. And you could fill the spaces between the gravel particles with sand. And so then you could say the beaker was full, except if you got and zoomed in close enough to see, you could see that there's a whole bunch of air voids, just like in this other beaker, between the sand particles. And in fact, there's just as many air voids pretty much in the sand, in the beaker of sand as there is in the gravel. It seems fuller because those are smaller particles, but when you start measuring, if you could measure all the volume of air that's in the sand beaker, there's just about as much in there. It depends how round the particles are, really. But otherwise, if they're all very, very round particles, the size of the particle still doesn't negate the fact that there's air voids in between them. And so when we make a concrete mix, we're trying to fill the voids between the gravel particles with sand. And then we're trying to fill the voids between the sand particles with Portland cement. And then we're trying to fill the air voids between the cement particles with water. And then what happens if you get an unbalanced mixture, you end up with too much water, you're filling beyond those voids. And so the same thing's true if you get too much sand, you're filling beyond the voids between the gravel particles. And so different mix designs give you different results. In general, the highest strength concrete mixes used in precast concrete have way more gravel as a percentage of the mix than they have sand. And they just getting closer to filling the sand, using the sand to fill those particles space of the air void space in the gravel. But in reality, is most concrete that you're going to use on a concrete slab on grade in a typical job site is going to have more sand than can fill those voids, and they're going to have more cement than you can fill the sand particle voids, and more water than you can fill up the cement particle voids. And so we end up with this unbalance because we also need it to be flowable and workable. But you get into a precast concrete plant where they've got steel forms and they can vibrate this stuff into submission. They can take a much harder mixture to work with and place it in place because of the nature of the equipment they have that we don't necessarily have access to, or not easy to use like that on a regular job site. If you're using wood forms, the wood forms can only be vibrated so much before you start to burst forms. And then you always have to worry about if you vibrate the stuff too much, you can separate the ingredients. So there's a lot to this. When we talk about rebar in the concrete, if you get like that picture I got at the very top here is looking at the column steel before they put the column form on it, pretty much, and that could pass the canary test, as we say in construction. A lot of times, if you got too much steel in there, you say, "Oh, I think that could pass the canary test." Well, it just means if you manage to get a canary inside that cage, canary wouldn't be able to get out. There's just so much steel there. Okay, so it's not particularly useful. It's just something you may hear on a job site someday. But the point here is that if you got a bunch of steel that's so tight there, you'd have a hard time getting certain kinds of concrete mixes to flow into between those steel particles. And so we have to choose the mix design that works for the application. And so on some job sites, you may have more than one kind of concrete mix. For these columns, you may have a different mix that maybe has small. If it's going to be that tight, you might have to have no more than 3/4 inch gravel, or maybe no more than 1/2 inch gravel. It's so tight, it's hard to imagine, that you could get all the concrete to go where you want it in here. It's maybe overdone in here, really. I picked that picture on purpose because it is so congested. It maybe is too congested, really, even from most mainstream concrete mixes that you would use. So you see the second bullet, I've got some sub-bullets in there. The largest aggregate must fit comfortably between the reinforcing bars and within the overall thickness of the concrete from form to form. So there's just 3 rules I'm showing in here, but there's a bunch of other ones that are used related to this. It says here the largest aggregate size should not exceed 1/5 the distance between the form faces. It should not exceed 3/4 of the space between reinforcing bars. So if you have the bars that are 1 inch apart, then you need 3/4 inch gravel, basically, for your maximum gravel size in your concrete mix. And then the third one was you shouldn't exceed more than 1/3 the depth of a slab. So if you've got a 3-inch slab, your gravel size can be no larger than 1 inch, but you have to satisfy all these things at the same time. And so sometimes by the time you get finished satisfying all the rules, and there's a few more like this, it could make you step down and have a smaller aggregate size. But the smaller the aggregate size, the more expensive the same strength of concrete becomes, because you have to add more cement to the mix when you bring the largest aggregate size of your concrete down. So I know I'm spouting a whole bunch of stuff about concrete here, but there's a lot to concrete to know, and I don't mean for you to have to know all of this. But yeah, common maximum aggregate sizes for concrete mix can range from 3/8 pea gravel up to 1.5 inches for the largest gravel size. And so when you buy gravel, it's usually related to, in the naming of it, it could be a 3/4 minus mix, which means the largest aggregate size is 3/4, and then it's well graded all the way down to smaller gravel sizes. Or it could be a 1.5 inch minus mix, where the largest nugget in there is 1.5 inches. Okay, so yeah, the mixture between sand and gravel changes the strength of the concrete in here, basically. And it fills as you're filling the voids. There's also lightweight concrete, and that comes from having lightweight aggregates. So the structural concrete is generally going to be lightweight concrete, or structural lightweight concrete will maybe roughly 80% or less of the weight of the concrete. So maybe, you could basically, you'll have, let's say if it was 100 pounds and you got 80 pounds, well, it's going to be more like 150 pounds is a common weight for concrete. So to see 80% of that in my head would be 80 plus 40, 80, 120 pounds. So yeah, 120 pounds. So actually, if I'm saying that, but you can kind of see it on the graph down here, normal weight concrete, and then you start stepping it down to structural lightweight concrete in the 120 down to maybe 100 pound range and that kind of thing. By the time you get down to insulating or fill concrete, then you're using volcanic aggregates. And then when you get down to the very lightest of concrete, you got vermiculite, perlite, kind of human-made kind of aggregates that are used like popcorn weight, real light. So not trying to get too much into the details, but why do we even care? Well, first of all, the concrete, why do we use lightweight concrete? Well, if it's lighter, it's got more air voids within the gravel nuggets, which means that you've got air voids inside of the nuggets, which means that you can make insulating concrete that actually can insulate and become kind of an insulation. So we can use that sometimes in places where lightweight also helps to reduce the weight of the structure on the top deck maybe. And so on the roof, when we pour concrete on the roof deck of a structural steel building, it's not uncommon to use a lighter weight concrete on that roof deck, whereas the other floors, we generally want the strength to not have the concrete break up. On a roof, you're just not having a lot of traffic up there, Water, if you can drink it, you can certainly use it to make concrete with, but you can also take the wastewater from washing out a ready-mix concrete truck and recycle that into making concrete. And so that's sometimes done, and that's not something that you'd probably want to drink. Then there's something, this is a mouthful, supplementary cementitious materials. So there are materials that are added to concrete as part of a kind of a partial substitute for the Portland cement. Some of the best ones actually have cementitious properties, where they are basically have hydraulic cementing properties like Portland cement at some level. So, and then there's some that are more about workability, kind of like the hydrated lime is in the mortar. You can have some supplementary cementitious materials that are not really adding strength so much as they are adding workability, which could be important. So the hydraulic cements generally are intrinsically adding strength to it. Okay, so a lot of the supplementary cementitious, particularly the hydraulic materials, they would be heated up just like the cement was in order to give it those hydraulic cementing properties. Okay, so this kind of blast furnace slag would be given with the main material that's used to make hydraulic cements. The fly ash used for pozzolans that's maybe a lightweight concrete and that sort of thing. And there's some other versions of materials that are used in concrete too. Anything beyond those four basic ingredients, the gravel, the sand, the Portland cement, and the water, anything else is considered an admixture, including, really, the supplementary cementitious materials I was talking about. So the Aaron Trayman I've talked about, but you can buy a separate additive that can be poured into the back of the truck, usually in a liquid form. There's a water reducer. There's a couple of different kinds of water reducers, well, several, really. The cheap poor man's water reducer would be Dawn dishwashing liquid or Joy soap that you'd use to wash dishes in the sink, the liquid soap. There's Cure accelerators that speed up the concrete set. Poor man's version would be a type of a salt. Most commonly we use calcium chloride. It is salty to taste because it is a salt. It's just not the same as sodium chloride. It's a calcium chloride. Salt is by definition the residue left behind when an acid and a base chemically react with each other. And so there's sodium chloride, there's calcium chloride, there's potassium chloride. These are all types of salts out there. So the one we call salt is not the only one. Now then, a Cure retarder slows down the set. The Cure accelerator, like calcium chloride, speeds up the set. We do that in wintertime concreting in cold climates because we're trying to keep the concrete from setting up keeping it from freezing before it gets a chance to get strong enough to deal with the cold weather. The retarders we are more likely to use down here to slow down the set of the concrete. The poor man's retarder is sugar, mostly in the form of molasses or maybe even cane syrup. Workability modifier could be something like hydrated lime or a supplementary cementitious material, the SCM, as I had it abbreviated. A shrinkage reducer. Concrete tends to shrink as it's setting up and at first, and it can be a significant problem at the beginning. Well, aluminum, or in its powder form, we call it alumina, not alumina, but I'm just trying to emphasize the on the end. So alumina can be used to combat shrinkage of concrete. It's mostly used in non-shrink grouts that we mix, not so much in regular concrete. But and then there are corrosion inhibitors that you can get. There's additives for freeze protection, and there's coloring. You can have a pigment in the concrete, and that's still an added mixture or an additive. The weight of ingredients, the main one I want you to know is the weight of the bag of Portland cement. I've got it listed up here again. These other weights are kind of useful to know, I think, but at the same time, I'm not going to be testing you so much on them. I think it's good to know that concrete weighs somewhere between 140 and 150 pounds. When it's freshly mixed, it's going to be closer to 150 pounds. After it's got a chance to set up, you'll have eventually less water in the mix, and it basically ends up weighing closer to 140 pounds. Just like asphalt is somewhere in that neighborhood too, of an asphalt paving mix. So anyways, you could go through that, but the red that I have down at the very bottom could be turned into a test question. That's the other thing on this page that could be turned into a test question. And it's basically, I'll start with the arrow that I have over at the second thing at the bottom. It says, if you separately add up the volumes of each of the ingredients of a typical concrete, a cubic yard of concrete that we have, when you measure those ingredients separately, you're going to get about 40 cubic feet. And when you're mixing, when you're measuring the volume of the gravel separately from the sand, separately from the Portland cement, separately from the water, you have about 40 cubic feet of volume in each of those separate ingredients altogether. And when they're all mixed inside each other and fill each other's air voids, you end up with 27 cubic feet of material in the end, in concrete. So that's the nature of your concrete mix. It becomes much denser because of those ingredients filling each other's air voids. So 40 cubic feet separately becomes 27 cubic feet of volume, 1 cubic yard, once they're mixed together. It's kind of a factoid that's kind of a fun fact, I guess you'd say. The outmoded volume metric or volume proportion mix design, which could typically, a very common mixture would be 1 to 2 to 3, where 1 is how much, 1 part Portland cement to 2 parts sand to 3 parts gravel. That's like 1 shovelful of Portland cement and 2 shovelfuls of the gravel, the sand and the gravel, which sometimes you'll have mixed together, sort of thing. But anyways, and I'm sorry, no, I'm saying 1 cement, 2 sand. I'm sorry, just pure sand. And then the third one would be the gravel. And when those are all mixed together, they fill each other with air voids, and you've got your concrete mix. And of course, you've got to also have the water, which might end up being a half a shovelful or whatever, or less. But anyways, yeah, let's see here. How am I doing on getting through this material? Yeah, okay, so that should be fine. 47 minutes, let's see. So basically, that's when we're dealing with volumetric, but nowadays, most concrete mixes are by a prescriptive method by weighing the ingredients, and I've mentioned that before. So and then there's also specifications that are part of concrete mixes where we measure the water-cement ratio. That's the weight of the water divided by the weight of the cement. Down there at the last sub-bullet at the bottom of the page, specifications often mention the maximum water-cement ratio of 0.5, 0.50. They often listed that as, or a slump of 5 inches, and a maximum aggregate size of something, those kind of things, as part of the mix design. So I've got a mix design right here that I was going to show you, and you can't read it very easily here on this page yet. I'm going to zoom in on it here a little bit. But this mix is considered a 3600 psi class mix. And what I mean by that is if you don't treat the concrete well, if you treat it the way most contractors treat it, you're probably going to end up with 3600 psi concrete. Now, if you do proper moist curing where you keep the concrete from drying out for the full 28 days, then instead of getting 3600 psi concrete, you can end up with 5380 psi concrete. That's like 50% more strength because you spent some time talking to it each evening and caressing it and making a friend of it. No, I'm making that all up. Bad joke, I know. It's, but if moist curing means you're keeping it from drying out for 28 days. So that's crazy talk. Nobody can do that. Well, I've seen a few cases where it's been done. I know of cases like that, and it really did change the whole arc of that concrete. It made it much, much stronger. You end up with a higher strength concrete in that case. 50% stronger. So here I am looking at that same sheet. I'm trying to get to it, but it's not letting me here. Okay, so I'm zooming in from here a little closer, and you can see now, can't really show you with a cursor here, just not working. But the class of if there is up at the top under the first double line that you see at the top, it says class is 3,600 psi. If you look down in the middle of the next section, it says the average compressor strength is 5,380 pounds per square inch, psi for pounds per square inch, at 28 days. Now that box that's down at the bottom where it says cement and fly ash and 3/4 to 1, 4 to 0, water, on and on. Anyways, the point is those are the ingredients in their proportions. So let me come to that. I'm going to zoom in just to that alone. So in this mix, this is a 1 cubic yard mix. So for every cubic yard, you have 500 pounds of Portland cement. Now notice the fly ash, that's a supplementary cementitious materials. They've got 82 pounds. So 82 pounds, that's their maximum. And that's somewhere around 7 or 8%, I think, of the cementitious materials would be fly ash. Okay, now there's a space and they go down to the next line and you got 3/4 to number 4. That's the gravel. So it's 3/4 minus mixed down to the number 4 sieve size or screen size. And then that's defined as the gravel. And then they got 1,764 pounds of it there. And then meanwhile, below that, they've got number 4 down to 0. That's the screen sizes in there. And they've got like 1,380 pounds of cement. And then the water, it's measured as 230 pounds. Now, they might not always weigh the water because they can look at volumes, but it would equivocate to about a certain number of gallons. A gallon of water weighs about 8 1/3 pounds. And so you could figure out how many gallons that is, by doing a little math on that. So down at the very bottom of this box, it says air entrainment agent, and it tells you which company and what brand or what model. Water reducer. So they have 2 additive. One with the air entrainment, we might have been added when somebody wasn't looking. The air entrainment's fine if you're using it on roadways. This came from the Oregon Highways Department. They're one of their concrete mixes, so it might have been on a roadway or something where it was used. The weight of the water in this mix divided by the weight of the cement, 230 pounds of water divided by 500 pounds of cement equals 0.4. And so 0.40, sorry, yes, 0.4. So the higher the number, the weaker the concrete. Because think about the ratio, it's going to become a bigger number if you're adding more water to the cement, right? So that's where it goes. So a lower number is a good thing. 0.4 is a pretty good number. And then you might have some jobs where they require you to be down to 0.3 or 0.35 or something like that. Okay. So too much water added to the initial mix makes the concrete weaker because it leaves behind air voids when the water is gone, when it's evaporated away or leached away. Too much water in the initial mix, like I said, but not enough water in the mix at the end. Once you place the concrete and it's starting to cure over the days and weeks, you want to keep as much of that water as you can in the mix. So these arcs are showing you that. In fact, what you can see in here is the solid line is talking about being cured the entire time and how it keeps getting stronger. If you were to go the full 28 days and then give up on moist curing, then that's going to change the strength too. But notice you're getting most of the strength if you can keep it moist cured for 7 days. And you're getting a lot of the strength if you can keep it moist cured for 28 days. So it gives you an idea.